I'd like to introduce Professor Linda Smith. Professor Linda Smith is a distinguished professor of psychology at Indiana University. And she was famous for her pioneering work in the dynamic systems approach to the development of cognition and action. She's published more than 150 papers and book chapters and won numerous awards, including the winner of the Society of Experimental Psychologists 2019 Norman Anderson Lifetime Achievement Award. I've been able to know Professor Smith a few years ago about her recent work on using a lot of using head cameras mounted on babies and toddlers to monitor their activities, and has been very interesting research. So Professor Smith, take it away, please.
So thank you all for having me here. And my contribution to our thinking about how to get common sense in artificial systems. So the question I want to begin with is, what does it mean to visually recognize a chair? This is a hard computational problem because there's lots and lots of different kinds of chairs. Now, the most dominant study or attempt to answer this question, at least right now, both in the study of human adults in experimental psychology and in computer vision, define the basic tasks that you're trying to solve when you go to recognize a chair as one of discriminating between chairs and all the other kinds of things. That is, the goal of learning is thought to be that what you need to do is find the decision boundaries that partition the space into many categories of discrete things. This is not an easy task, and despite their many, many remarkable successes of AI in using this approach, it's sort of become increasingly apparent that there are substantial limitations. And sometimes these limitations are suggested as indicating that the system lacks common sense, as for example, might have difficulty recognizing a chair being used for some unusual purpose or in some unusual position, or an entity that is both a chair, that's Bronte's chair in England, or also is just a rock. Another example in this question of visual object recognition of lacking common sense is the question of what happens if you come across something you've never seen before. What do you do? A system that has learned to discriminate categories is typically forced to make a decision. And so if they were to encounter a lobster for the first time, they would be forced to find the category or would be pulled to the category to which it was most similar, since it's about boundaries. But if you take a toddler and you show them their first lobster, that toddler, most of us humans don't have this problem at all with things we don't see. We would instead look to someone and say, what is that? Okay. Knowing that it belongs in some category you don't know. That's common sense. They have no trouble, even young children, knowing what they don't know. Your average 2-year-old also does something that is pretty remarkable and is often talked about as a form of one-shot learning. So for example, if you were to, that picture up there, that might be Uncle Eddie, okay? So maybe you go to a family picnic event as a 2-year-old and you've never seen Uncle Eddie, never met him, he's never showed up at a family event before, but there he is all day and he has a picnic with you and talks with you, and he's a pretty funny guy, so as a 2-year-old you like him. It's highly likely that from that day forward, if he doesn't show up for the next big family event 3 months or 6 months later, that you will recognize Uncle Eddie. One experience. And you'll recognize him 3 to 6 months later, even if he's changed his hair a little or grew a mustache. You might even show the remarkable ability of looking back as a 2-year-old into your parents' wedding pictures and recognizing Uncle Eddie at the wedding when he was, 10 years younger. Children also do this with objects. Which anybody who has a 2-year-old would know experiences this all the time. It's why they seem brilliant. You go somewhere that you've never been before, maybe to Indiana, nice place, but you come from an urban area and you've not, your child really doesn't know much or seen any tractors, but he watches a big John Deere work in the field very hard, doing good work, plowing, and your 2-year-old is just fascinated by it, watches it. One tractor. From that day forward, that child will recognize antique tractors, toy tractors, different brands of tractors, pictures of tractors. They won't include they won't include other kinds of farm equipment or trucks or Jeeps. They will exclude those, recognizing pretty much tractors, including in the tractor category, all the same things. How do they do that? Okay. This is in some sense perhaps not a form of common sense, but a form of brilliance. But it is within the repertoire of just about every healthy 2-year-old child. So the question we want to ask is, what kind of learning system could show the nuanced common sense and rapid learning of a human toddler? Well, learning and having a functioning learning system depends on both the learning machinery and on the training data. Most people spend their time worrying about the learning machinery. Can they build a better architecture? Can they change the loss function? Can they do this? Can they connect it to something else? But I think actually we should all think first about the training data, because the training data defines the task to be solved, and it actually is the source of the solution. And it should constrain, in some ways, the learning machinery. So what I have been doing for the past decade is trying to understand the training data that makes 2-year-olds as smart as they are. And what we've done here is we have taken an egocentric, I don't know why this automatically switched, I wasn't ready, but it did it. We've taken an egocentric approach in which we have, what we want to do is understand the visual world from the child's point of view, because the child's point of view is not the same as yours. They have a different body, a different size, different biases, they're in different locations. So the egocentric view, what you see, the regularities, the frequency, the structure of the visual data in front of you is biased and selective. It depends on your posture, it depends on where you turn your head. So for example, for this infant in this image here, who's being fed by his mother, that child at that moment can see the mother sitting on the chair, but he can't see the clock on the wall or his father loading the dishwasher or the person at the sink or the dog. Now you could say to yourself, he might turn his head and then he'd be perfectly well able to see all that stuff. But if he's biased not to turn his head, or if he lacks the motor abilities to turn his head, that information is not there, okay? The other thing about egocentric vision is it reminds us that the input is infinitely variable, okay? So this is just one every 5-second view in time of a child's view of their own sippy cup. That sippy cup, the image projected to the eye from the sippy cup, depends on the relationship of the child's eye, which is in the head, on the body, to the sippy cup. And it's infinitely variable, hardly ever repeated. Okay. The egocentric view brings us home to what are, I think, the two core and classic unsolved problems in visual object perception. The first problem is what the textbooks sometimes call object constancy. How do we recognize an individual object as being the same thing, despite the continuous and marked variation in the image that can be projected from that thing to the eye, the continually varying, never repeated image that's projected to the eye. That's the start of vision. The second question, second core and classic problem, is how do we manage to recognize the many thousands of categories of things, given their indeterminate number of instances, and then keep continuing to learn and rapidly learn new categories. In general, right now, the field treats these two problems as quite separate, okay? They don't really think about them as exactly the same thing, how you recognize your sippy cup from all the ways you can see your sippy cup and how you categorize all the possible cups in the world. But my hypothesis from looking at the egocentric experiences, everyday experiences of toddlers, is that these are fundamentally the same problem for the visual system, and that solving problem one, how we can recognize the continually changing images projected from a single object, actually solves problem two, and one-shot learning just about falls out of that, and that's why it's so easy for 2-year-olds. So the first thing that when you look at the egocentric data from babies, okay, and toddlers as they explore the world, the first thing you realize immediately is that the individual object is the unit of experience. So when we go to teach categories, typically in psychology experiments and to CNNs, what people do is they gather as many variable possible cups as they can find. They can get them in hard conditions, like ObjectNet, or easier conditions, but they get a whole variety of different cups. What you want to do is get as many different cups as you can and teach them along with as many different bases as you can and as many different chairs as you can, because what you need to do is find those boundaries. Okay? But you know, this is not how we experience the world. We do not, we even as adults don't experience the world this way. If we were to go, how does it work in the morning when you get your coffee cup, right? You go to the shelf, you take that coffee cup out, okay? You might see a bunch of shelf coffee cups there, but then you spend the rest of your day carrying around that one coffee cup, filling it, refilling it, drinking from it, putting it here, putting it close, sticking your papers on it, including it sometimes. You project from that one coffee cup you actually drink of a whole lot of data about that coffee cup. And the ones in the cupboard that you glanced at, they're not giving you very much information. So this is just, again, this is from our head cameras from home view, which the babies have worn in their home. And what you see here is the variability that these are from 4 different babies, 4 different little segments of sippy cup images. A lot of different views of their sippy cup. In clutter, partially included, easy to see, hard to see, good light and bad light. So these insights, most of the insights I'm going to talk about today come from what we call the Home View Project. This is funded by National Science Foundation, which was very brave to fund us the first time around, and they funded us a second time around. We have so far collected a corpus of developmentally indexed egocentric scenes from 101 infants for the first 2 years of life. These are, we were aspiring to get day-long recordings, but they go between 4 and 7 hours on the whole. There are no experimenters present. The cameras are embedded in the hats, and which their families are given, and all they have to do is get the camera lined up right over the eye. And we have lots of data. Okay, wait a minute. Next. There we are. So the first thing that you learn when you look at these data is that in the 4 to 7 hours that an individual child generated in a day, there is massive experience about individual objects. So these are images from the sippy cups from one toddler who contributed 7 hours of head camera data to the home view corpus. And in 40% of the images, 40% of those 7 hours, this one sippy cup was present, okay? That's a lot of data about what that sippy cup looks like, okay? And this is not probably unusual. What do you think in a day some toddlers' view of their own shoes look like, okay? or in a day some toddler's view of their teddy bear or blankie looks like, or their mother, okay? Massive amounts of data about a single object. Now, we also know as developmental psychologists that this baby is probably expert on finding that sippy cup upside down in the dishwasher, half occluded under a blanket, in good light and bad, far and near, okay? But the thing is, we also know, because of the one-shot learning that they showed, that this child is probably not going to overfit their notion of cup to their one sippy cup. So what are these? One thing to think about is, what are these massive experiences of a single object teaching? Well, they're likely to teach things like segmentation, like finding it in clutter, building strong visual memories. So much experience is going to, with one individual object that you know and want and are very much interested in, is likely to teach some really basic principles, okay, that are important to vision and seeing objects. It's not just sippy cups that are, everything in babies' everyday worlds are organized like this. So you just need, for example, these are the frequency of faces in babies' views from 0 to 12 months. And what I'm showing on the y-axis here is the proportion of frequently appearing faces. So how many faces do you need to account for all the faces recorded in a day, okay, for these babies? Over the first year of life, you only need 3 faces. Let's say mom, dad, and grandma, okay? Just 3 faces. But they're going to be able to recognize Uncle Eddie from one day by becoming experts, real experts, on 3 faces. And this isn't just an oddity of US nuclear family homes. We've collected data in an impoverished village, fishing village near Chennai, in which there's minimal electricity. Most cooking and daily life is done on the street. And so you might expect that these babies would see many more faces. But the babies in India over the first year of life, just like the babies in Bloomington, Indiana, see predominantly 3 faces. This is the proportion of all faces on that y-axis that can be accounted for by the 3 most frequent people in the US in blue and in India, in that village outside Chennai in orange. Okay? Partly that's because of the highly selective nature of egocentric vision. If there may be a lot of people on the street, but if you're mostly being held or care about in that first year of life, mom, auntie, and one other person, that's who you're going to see, even though those other people are physically quite near. All right. So all this suggests, and if we'd ever thought about it much, it'd be obvious, that the individual object is the unit of experience. And this is true, the fact that you have experience with individual objects at a very high frequency, a few individual objects at a very high frequency, and most objects at a minimal experience. That is true over multiple timescales. It's true when we look over months and years, like what are the faces most frequent that you're going to see? They're going to be pretty common people throughout a child's lifetime. It's true within a day and across months, like the time your sippy cup, which you love, you're going to see it, or your shoes until you change up a size, right? It's also true in the seconds and minutes of interactions with objects, which is where a whole lot of learning may happen. So I'll talk about this. So these are data from a study in which we took parents and we brought them into a room and we dropped 33 toys on the floor. And we gave parents and their children, their toddlers, 12-month-olds, 10 minutes to play with these objects. Now, in principle, they could have played with every object in the room for a few minutes, just flitted about from one interesting thing to another, but they don't do that, okay? What they do is they pick up one object, they play with it for an extended period of time. They pick up another object and they play with it an extended period of time. They might go back to the first object, play with it, go back to a second object and play with it. with all of this extended in time. And what you end up with, again, is a frequency distribution over this 10 minutes of play in which a few objects, this is the frequency of child handling an object as a function of the rank order of frequency. And the most frequently played with object is very frequently played with, and the second and third pretty much as well. But by the time you get down to the 10th most frequent object and out, they're hardly played with at all. These children handle 2 to 5 objects in 5 minutes, individually object-based, not sampling everything. Their parents do the same thing, shown in the second graph, and the objects that the parent and the child play with frequently are the same. So the most frequently played with object is typically the most frequently played with object for the mother and the child, okay? And this just displays how they extend this play in time, that they're playing with one object, go backwards, playing with one object for an extended period of time. On average, the most handled object by the child in this 10-minute play session, or most handled object by the parent and child in this 10-minute play session, takes up 4.1 minutes of the 10 minutes, okay? Just think of that, 4.1 minutes. That is a big packet of data about a single object. A whole lot of data about a single object, okay? So, point 1, the unit of experience, if we're going to understand common sense about objects, is probably not a big data set of all the instances you can find or even hard instances in ObjectNet. It's about individual objects. The unit of experience that makes us smart and nuanced about objects is about individual objects, one at a time, and we learn a lot about them visually. So the next question we want to ask then, or we need to ask if we're going to take this approach, is what is learned from all these infant-generated images of an individual object? Well, the thing that's interesting is the images generated by an individual object can vary infinitely, okay? That's why that core problem of how we recognize an object under all the lighting conditions, occlusion conditions, rotation conditions, near and far, is such a critical problem in vision. But importantly, although the variation is infinite, it is principled, at least partially. It is what we're going to see of an object is constrained deeply by the 3D geometry of that object. And what we have been discovering in looking at the structure of children's egocentric views of objects as they're actively interacting with them is that those geometric constraints on objects are reflected in the structure of the projected image in ways that I think are very, very clear. So that what you're going to see in the projected image depends on the geometry of the object, constrained by the geometry of the object, and by the spatial relation of the perceiver to the object. So one of the first results is when babies hold objects, if you give babies objects to play with, you would think they might generate every possible view you could see of that object, but they don't. They generate highly biased views. What these heat maps show, they show changes over developmental time. If you're really interested in this, this is probably the main paper, the one in Journal of Vision. They show changes between a year and 2.5 because the biases get stronger, but they're basically the same biases. These hotspots in each of the images are what are known as planar views. Those are the views in which the longest axis of the object is either perpendicular or parallel to the line of sight, okay? So whatever the longest axis is it perpendicular or parallel to the line of sight, okay? That's what those hotspots are. And you see this kind of mush between all the hotspots. That's because babies are actually biased to rotate objects when they're playing with them in depth. They could rotate them other ways, but they don't. Rotating an object in depth probably provides the best information about three-dimensional structure. So there's one bias. Another thing that we've done is we've looked at what the 2D image looks like and what the properties of the 2D image are, not with respect to the 3D object first, but just with respect to itself. And what we've shown is the variability in the mask orientation predicts whether children learn object names. So what I mean by that, so the mask is just the pixels that belong to the object. All occlusion, you don't make any inferences about the object. You have to just go by the 2D images. No inferences about, those are hands on the objects. Just give me the 2D mask, because that's what that baby has to start with who doesn't know anything. And what we measure is the most elongated axis of the mask, okay? And the degree of variability in the image of the most elongated mask predicts object name learning. I'm going to say more about this next after talking about this. The other thing we found is that this is a multidimensional scaling, two-dimensional compression of the pixel-to-pixel similarity of every generated image of a football helmet. And what you can see is the images the child generated of this toy football helmet. In the pixel-to-pixel similarity, there's a lot of objects that are images that are very, very similar to each other, okay? Dense cluster of highly similar objects and a whole surrounding of not very similar objects. In our models, we used sort of some standard off-the-shelf CNNs, AlexNet, and one other that I can't remember. And we showed actually that the baby's generated images led to better learning than did adult images when they were exploring these same objects. And we also showed that even when you kept frequency constant, that a network that was trained on a dense cluster and the outliers learned and generalized better than a network that was trained on a uniform sampling over the whole space, or one that was only trained on the outliers. That suggests that there's some useful information in this dense cluster of highly similar objects and highly similar views of an object, and the outliers, that both are probably contributing. One of the things we've been thinking about is that these objects here in the dense cluster probably have the highly informative properties. And so what we need to know is what those properties are, and that maybe these outliers help generalization by sort of the outer reaches of what's possible in the projected images. You need to sample that. One of the ideas we're working on right now is that this right here, this dense center, contains a link between the 2D object and the 2D mask. Between the 3D object, the 2D mask and the 3D object. So let's see if I can make this point. So object views, when we talk about the object views or pose of the object, some people talk about it as if it's a stimulus property, but it's not a stimulus property. The stimulus is the 2D projection onto the retina. It's really about the world. Object views are defined by the spatial relation between the perceiver and the 3D object. I've just told you that babies are biased to these views that are defined in terms of the major or most long axis. Well, what we've also found, and I think this could be a really important discovery, and actually I'm talking about this for the first time, you guys are the first to know, that babies are actually biased. Forwards. Babies are actually biased to create images in which the longest axis in the image is actually close to the major axis of the object out in the world. That means that they're not perfect, but that means they are giving themselves a frame of reference. If they're biased, that's probably what this rotation and depth business is about. If they're biased, to maintain a relationship between the extended axis on the retina and the major axis of the object, that means they have a frame of reference at the 2D level by which to integrate images around that axis. All right, and so that brings us to shape. And as most of you probably know, shape is how we do things. It's very, very important to human cognition and vision, but it's not well understood. Although we would see all three of those chairs as chair-shaped, there's a lot that's different about them. It's not obvious why they're chair-shaped at all. And I would say that there is actually in psychology no well-accepted theory. There's a well or deep understanding in the neuroscience level either exactly what makes us see things as having the same shape. But we do know from many, many, many different labs, not just my work, many, many, many different people, that active visual experience in the 3D world is what enables toddlers to recognize objects from unusual views. It's what enables them to generalize to new instances of a category. Playing with one chair helps you generalize to knowing it's another chair. And we know that it helps them recognize the abstract geometric shape common to a category, so that they can recognize it from shape caricatures just made out of a few different volumes stuck together. So we know somehow, even though we don't know what shape is, we know what 3D shape is. We know somehow that active experience is playing a role in it. So here's what my hypothesis is. This is how we get one-shot learning in tractors and faces. The hypothesized path is this, that the packets of toddler-generated visual data from a single object teaches the visual system how to recognize the object across variable and challenging contexts. And this learning generalizes to shape similar things, okay? So the child has a packet of data about their own sippy cup, okay? And that enables, that packet of data, that's what enables if I put the sippy cup in some hard to see place, that they would be able to robustly recognize it, even in clutter or with partial occlusion. But what's enabling them to do that is whatever, we don't know quite what it is whatever they've managed to learn about shape, contour, three-dimensional, so forth. And of course, that will generalize to a shape similar thing. They'll be able to recognize it as well. If that's true, then it's very easy for, given that they know this is a cup, to also immediately know that that's a cup. This is one-shot learning, and it's not even very magical. It seems very straightforward. It seems like it would have to be true, okay? And it would also enable you, of course, the same kind of learning from a single packet to be able to recognize chairs in unusual contexts or circumstances without much work. The idea then is that we might gain a whole lot if we just stop training on so many different images and maybe settle down to training on just a few really rich, highly variable, massive amount of data about one or two objects. And so this is, I just said that, but I'll say it again. This is what I think how we get the one-shot learning of that characterizes 2-year-old children. Now, before I conclude, I want to, oh, no, I'm not ready there yet. I have a couple more things I want to say. So I began this talk by saying that learning depends on both the learning machinery and the training data, because that defines a task to be solved, okay? And when we go and we look at that data from the point of view of a young child, it strongly suggests that individual objects are the unit for learning. And it strongly suggests that it's not really maybe foremost, or at least not originally, about discriminating categories, but maybe foremost and most originally about how images projected from a single object can vary. And what this gives us is principles for recognizing individual objects. And it may give us generalized principles for how we can recognize any object from a variety of projected images. and it gives us shape. And if these ideas are right, I mean, they're not well totally solved or totally shown as of yet, but we're working on it. What they will do is they will unify the two core problems of visual object recognition, how it is that we recognize individual objects as being the same, despite the continuous variation of the 2D image projected from the object, and how we manage to learn and generalize categories and do so quite rapidly from a single example. This is a point that I was hoping if I had enough time, I would get to say something about. And that is, there's a fourth point that I want to say about where I think the nuance comes. And that is that if we would, that babies, the kinds of visual experience that babies have, they change with development, and they change with what I think in a very important way that may have provide deep insights to how the human visual system is so smart. So the young babies, if I were to look at 1 to 3 month olds, they would not be generating images of objects rotated in 3D depth. They couldn't possibly, because they can't do anything. They're just kind of looking around at the world. A lot of faces. The sensory motor development of children creates a kind of curriculum of visual experiences, which is centered on different kinds of contents. We also have new and very exciting, I think, data, well, it's exciting to me, data that may change how we think about things, that shows that sensory motor development, the changes in sensory motor development don't just change whether you're looking at faces or you're looking at objects. It actually changes the correlations between low and high level visual information. And let me give you the example that we're working on. So one of the things we notice from whole view right off is that the contents of babies' head camera images in their everyday home life change pretty dramatically with age. And one big change is the relative frequency of faces and hands. So for very young babies, faces make up about 25 to 30% of every frame. There's a face, 25 to 30% of every frame. That means 15 minutes out of every hour is a face, okay? That's a lot of faces. But by the time you're approaching just after your first birthday and by 2 years of age, the frequency of faces has dropped a lot in these images. It's down to about 6 minutes an hour. But what's happened is it's not that people aren't around, it's that the proportion of hands, both your own and others, are the primary object, a body object part in these images. So their hands, your own or other people's, are very rare in young babies' head camera images, but they're very frequent in a 2-year-old's head camera images, close to 20 minutes for every hour, okay? Now, these hands in these images, they're not hands hanging in the wind, they're hands on objects, okay? So early on, you have young babies have a whole lot of faces in their images, and older children have a whole lot of hands, their own and other people, acting on objects, okay? So this is a content difference. Faces early, hands later. But it's not just a content difference, okay? Early on, when you look at all the images with faces, you find that they have a pattern that looks much, much better than most other images that those babies just happen to see. That all the contrast is centered in the center of the image. That's what faces look like. For, you know, if you put this is 60,000 images, 0 to 3 months here. And the high contrast is centered in the image, okay? When you get to older infants, where you see the high contrast centered is not for faces, it's for objects, okay? So what this means is that there is changing content with age. That's what this figure shows, some of what we know. Changing content, so faces are declining with age, hands are going up with age. Changing content. But that changing content is also correlated with properties of low-level features, with contrast, with spatial frequency, with the number of line orientations. Why is this important? Okay. Because this is the stuff out of which top-down recurrent connections, you know, as a face goes down and can put the gain on the contrast, put the gain on the information in the right place. This is the stuff. You need correlations between top-down and low-level content. If you're going to high-level and low-level content, if you're going to get top-down recurrent networks that can actually be smart and nuanced, okay? So I wanted to put that in as one last little point. So to conclude, I think we just need to change, can't help myself. We just need to change everything we think about the problem of object recognition. That's basically what I'm saying. Thank you very much.
Thanks a lot, Linda. Great talk. It's fascinating as a machine learning person to see that all this data that looks very similar to our data augmentation process. Okay, so now we have quite a few questions. Let me start with one of the questions. I don't think we have time to for you to answer all of them live, but let me start with one of the questions. This is from Laurie. Could some of this useful bias towards some informative views be constrained by motor control, size of hands, weight of objects, or rather ease of focusing the eyes on a long axis, x-axis versus a long y-axis?
Okay, so we actually have data that answers that. So the bias to rotate, the bias that in terms of how you look at the object, right, could be a bias about hands, okay? That is the easiest way to grasp objects and do things with objects. So that's absolutely a correct assumption, except it's wrong. We took objects and we put them in 3D plexiglass spheres so that they were equipotential to what the hands could do, as opposed to, and what you find is the biases are stronger. The hands are getting in the way, okay? The problem with young kids is they can't move them the way they want. So the bias is stronger and more powerful at younger ages than it is at older ages if you put the objects in a sphere, okay? I think it is strictly I think it is principally a visual bias. But the sphere studies suggest that it might be.
Thanks. The other question I'd like to get to is Aaron Sloman had a question. Could you unmute and ask your question?
Okay, so. Okay.
Can you hear me?
I can hear you.
Well, very nice to meet you again after about 13 years.
Yes, been a long time.
A brilliant talk, but I kept thinking, how would this generalize to blind babies? And thinking about what I remember about newborn babies, not as a psychologist, but as a curious and inquisitive parent. And there's a huge amount of stuff being put in mouths, excuse me, and manipulated, which means that there's tactile, haptic, and continuous changes of various kinds being correlated through different channels. And I suspect that insofar as babies born blind can become cognitively pretty richly developed and able to cope with their environments, there must be something deeper and more general than all this emphasis on vision. Vision would then be a special case.
Okay, I think you're profoundly wrong on that. Okay.
Oh well.
So I actually have quite a bit I'd like to say about this. Okay, because first of all, one of the great things about human development, and I think biological development, is that it finds a way. Okay. Yeah. So there's this book, and it sounds like an odd book, but I think it's written by Mark Blumberg, who is a developmental neuroscientist who studies rat development. He does very, very good work. But he wrote a book because he felt people didn't understand how much development itself is an adaptive process, and how there's a sense in which people are always looking for some deep inner Platonic truth that people can manage it across different contexts. And what his book is called, it's a wonderful book to read, it's called Freaks of Nature. And what he did was look at all those cases where someone's born, these were animals as well as not people so much, but sometimes. He had a few cases of people, but mostly it was animals, born without a leg, or the two-headed rattlesnake, or all these oddities that happen, okay? And what do we know about those oddities, okay? The three-legged dog will run. He will find a way, okay? Yep. The two-headed alligator finds a way to feed himself and manage it, all right? Because we are adaptive systems, and we're going to keep changing and find solutions. And it's one of the geniuses, okay? So when I hear, when I think about sign language and deaf children, I don't think about it actually the way other people do. Other people think that means we must have some platonic language in there that just can drive out through anything. I think, heck no, look at how amazing we are. We have a system that evolved to do this through hearing and speech. We know that there's all kinds of pressures on it, but you know what? If you mess that up, we are so good, okay? As generalized learners, that we will find a structure and find a way. There are multiple pathways to the same end, okay? So that's what I would say about development. Doesn't mean some deeper, higher truth has to be true of sighted babies, because blind babies can do it too, okay? Blind babies do it too. Now, the more, I think it is interesting, the haptic information, because we know from adult visual systems that haptic processes, okay, feeling objects, has direct pathways into and influences part of the ventral stream. And so there's very interesting connections there. And we know that they're mingling in our representations as adults and our recognition of objects. I have done nothing on what the haptic information is at that level that would be useful here, but I don't doubt that it's there and that it's probably doing a fair bit of work.
Yes,
Right.
Well, there's a lot to talk about, but we won't have time now, I think.
Right. Yes. Thanks. Thanks for the great question and the great answer. Maybe you can talk more afterwards. And let's thank Linda again for her amazing talk.
Well, thank you all very much.